बिस्मिल्लाहिर्रहमानिर्रहीम। तो आज जो हम विल आर गोइंग टू स्टार्ट ए न्यू पार्ट ऑफ द स्पेक्ट्रोस्कोपी विच इज़ अल्ट्रावायलेट विजिबल स्पेक्ट्रोस्कोपी। अभी तक जो हमने पढ़ा रोटेशनल वाइब्रेशन, आज हम पढ़ेंगे अल्ट्रावायलेट विजिबल स्पेक्ट्रोस्कोपी। तो अल्ट्रावायलेट विजिबल स्पेक्ट्रोस्कोपी में बेसिकली जैसे हमने रोटेशन में देखा, देयर इज रोटेशन ऑफ द मॉलिक्यूल which actually means that molecule gets transited upon absorption of a particular wavelength from one energy level to the next. इसी तरह से IR में हमने देखा that IR spectroscopy में there is molecular vibration। और हम ये कहेंगे कि जब वो मॉलिक्यूल IR रेडिएशन एब्जॉर्ब करता था वहाँ पे, तो that gets transited from one vibration level to another। यहाँ पे भी it leads to the electronic transitions। तो इस स्पेक्ट्रोस्कोपी में we have electronic transitions। इलेक्ट्रॉनिक ट्रांजिशंस दैट मीन्स यहाँ पे जब मॉलिक्यूल्स और यहाँ पे जब मटेरियल एब्जॉर्ब करता है रेडिएशंस विच आर अल्ट्रावायलेट और विजिबल रेडिएशंस, सो इट लीड्स टू द इलेक्ट्रॉनिक ट्रांजिशन। इसका मतलब कि इलेक्ट्रॉन्स ट्रांजिट हो जाते हैं फ्रॉम वन एनर्जी लेवल टू द नेक्स्ट। जब उनको एक पर्टिकुलर दिस इतनी एनर्जी डिफरेंस की रेडिएशन मिल जाती है in the UV-visible range, they absorb that and then it leads the transition from one level to the next level, higher level. So that is equal to E is equal to E2 minus E1. तो हम ये कहेंगे in the UV spectroscopy there are electronic transitions and the radiation used is either ultraviolet or visible, जिनका रेंज हमने पहले भी इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम में स्पेक्ट्रोस्कोपी के बिगिनिंग में किया था। यू कैन फॉलो द सीरीज, जिसको कोई क्लास मिस हुआ हो कैन फॉलो द सीरीज। हमने कंप्लीट स्पेक्ट्रोस्कोपी का पैकेज इसमें जो है शॉर्टकट बड़े कंसाइज मैनर में दिया है। तो यूवी के लिए जो रेंज ऑफ वेवलेंथ है दैट इज अराउंड 200 to 380 नैनोमीटर्स। विजिबल के लिए जो रेंज है दैट इज 380 to around 780, around 760, 780 nanometers। इसका वेवलेंथ ये रेंज है। whenever molecule absorb either this radiation or this radiation, it leads to electronic excitation। तो अब हम कह रहे हैं कि there is electronic excitation, that means molecule is actually absorbing energy। electrons there are different types। एक मॉलिक्यूल में इलेक्ट्रॉन डिफरेंट टाइप्स से होती है। फॉर एग्जाम्पल एक मॉलिक्यूल है हमारे पास, I'll take an example। ये एक मॉलिक्यूल है, हम जानते हैं दिस इज अ कीटोन मॉलिक्यूल। कीटोन मॉलिक्यूल में ऑक्सीजन पे लोन पेयर होता है। ये बॉन्ड दिस इज अ सिग्मा बॉन्ड, दिस इज अ पाई बॉन्ड, दिस इज अ सिग्मा बॉन्ड, दिस इज अ सिग्मा बॉन्ड। इसका मतलब है व्हेन दिस मॉलिक्यूल एब्जॉर्ब्स ultraviolet or visible wavelength radiations, it leads to electronic transitions। The electronic transitions, it can be transition of the electronic transition, it can be transition of sigma electrons, कि sigma electrons will undergo transition, sigma electrons, or it can be transition of pi electrons, it can transition of these lone pairs, non-bonding electrons or lone pairs, note by n। तो electron transition में it can be transition of sigma electrons or transition of pi electrons or transition of electrons from one energy level to the next energy level। Now before एक topic है, we'll deal this later, the types of electron transitions, that will be a topic inshallah maybe in the next class। So today we'll deal with एक important law होता है which actually guides the absorption of radiation in the ultraviolet visible spectroscopy। तो उसमें क्या होता है, बेसिकली हम कहते हैं कि molecule absorbs the radiation, ठीक। Once it absorbs the radiation, then only there is electronic transition। ये जो absorption of radiation है, this is governed by a law। So the absorption of UV and visible radiation is governed by a law called as Beer-Lambert law। बहुत important है Beer-Lambert law। तो टुडे हमारा मेन फोकस होगा Beer-Lambert law। So we'll rub it here so that कि सब पूरा हो जाए इसमें. So Beer-Lambert law. अब Beer-Lambert law basically concept दो का है. तो Beer-Lambert, two scientists, Beer-Lambert law. ये लॉ बेसिकली कंबाइंड हुआ बीयर्स लॉ एंड लैम्बर्ट्स लॉ. तो पहला जो था दैट वाज लैम्बर्ट्स लॉ. पहले हम लैम्बर्ट लॉ देखेंगे, फिर बीयर लॉ, फिर विल कंबाइन दैट. तो लैम्बर्ट ने कहा था कि जब भी किसी सैंपल पे जो है रेडिएशन पड़ती है, जैसे कि एक सैंपल है, एक लिक्विड सैंपल मान लेते हैं हम, अंडरस्टैंड. जब उस पे अल्ट्रावायलेट विजिबल रेडिएशन पड़ती है, लेट अस से इसकी इंटेंसिटी जो है दैट इज आई, take it as I, ठीक. Let's the intensity of radiations I0. It will absorb radiations, some portion. कितना absorb करे, we don't know that. So now let us say कि this is the portion of radiation that comes out. क्योंकि जो radiation that will come out had less intensity, क्योंकि कुछ intensity absorb हो गई इसमें से by the molecules. तो as per Lambert's law, there will be decrease in the intensity of the radiation which comes out of the incident radiation. As per Lambert's law, when a beam of a monochromatic radiation, एक radiation इसका एक single wavelength है, when that actually passes through a homogeneous medium, homogeneous means इसमें particle size एक जैसा, इसमें कोई cloudness नहीं, it's a particle size एक जैसा. It passes through a homogeneous medium. The energy is absorbed and the rate of decrease of intensity of radiation with the thickness. Let us see इसकी जो है thickness of this container, that is let's see it is dx. इस container की thickness, इसको इतनी जो है पास होना है यहाँ से, passage के दौरान जो है it absorbs the radiations. ठीक है. तो as per the Beer-Lambert's law, so the decrease in the intensity of the radiation with respect to thickness once it passes through a medium that is directly proportional to intensity of incident radiation. तो हम ये कहेंगे the decrease in the thickness, ठीक, that is the decrease in the intensity of this radiation. We'll keep it I. यहाँ पे let us see जो है intensity is, और हम इसको decrease in the intensity of this incoming radiation, इसमें से कितनी decrease हो जाएगा with respect to thickness, जितना thickness ही pass हो रहा है. According to this it is directly proportional to the intensity. जितनी radiation की, अभी यहाँ पे थोड़ा कंफ्यूजन को रिमूव करने के लिए let us don't keep these radiations. हम सिर्फ ये कहेंगे कि ये जो है रेडिएशन इसकी इंटेंसिटी आई है, जिससे फिर कंफ्यूजन पैदा हो जाता है. सो इस once this radiation passes through the medium, it comes out, that will be of less intensity. So कितनी इसमें डिक्रीज हो जाएगा इनकमिंग रेडिएशन में इंटेंसिटी, दैट डिपेंड्स ऑन द इंटेंसिटी ऑफ रेडिएशन. जितनी ज़्यादा इंटेंस करोगे उतना ज़्यादा decrease होगा. So this law, it becomes, if we remove this proportionality, we'll see that is equal to k, some constant at I. This is called as a Beer's law. So this is the intensity of the radiation, incoming radiation. This is the constant, and this it's actually called a constant. So the decrease in the intensity is actually is equal to product of the constant and the intensity. Now, अब हम अगर ये मान ले कि इसकी इंटेंसिटी इंसिडेंट रेडिएशन की I0 थी, जो यहाँ से निकल रहा है रेडिएशन, दैट्स I0. Now we'll do the integration of this and this. Integrate this and this. So now before integration, now what we'll do, we'll separate this. यहाँ से हम ऐसा करेंगे, इसको थोड़ा सा रिशफल करके I by I, that is equal to k dx. मैंने इस टर्म को जो है यहाँ पे लाया, that becomes this by this by k dx. अगर ना उसको तो लिमिट्स के बीच में विल इंटीग्रेट फ्रॉम, इसकी थिकनेस इट्स फ्रॉम 0 to x. that is total thickness is x. So it goes from this to this, and then इसकी initial intensity goes from I to I0. तो जब इसको सॉल्व करेंगे you will end up with, so 1 by x dx is log of x. You will end up with log of I0 by I. याद रहे कि आई एम नॉट गोइंग टू डेरिवेशन, क्योंकि हमारा वो मेन पॉइंट ऑफ इंटरेस्ट अभी नहीं है फॉर द ऑब्जेक्टिव एग्जाम्स, looking at the situation. So it becomes the log of this, it becomes kx by 2.303. ठीक, तो ये जो फैक्टर है इसको हम लिख लेते हैं a. This factor is a. ठीक, now this factor is a, so that is equivalent to now this factor is a, so that we can say a is equal to kx. अगर हम इस फैक्टर यहाँ ले जाएंगे, it becomes natural log. ठीक, so it becomes 2.303, या ऐसे लिख ही लेते हैं, it becomes 2.303 log of I0 by I. इसके लिए हम टर्म यूज करते हैं एब्जॉर्बेंस, दैट्स A. सो A एब्जॉर्बेंस, दैट्स कॉल्ड K multiplied by X. Now this is actually in a nutshell the Beer's law, Lambert's law, that the absorbance of radiation absorbed by the medium, that is actually directly proportional, that is called product rate constant multiplied with thickness of the medium. So ये तो हो गया Beer's law in it will be Lambert's law in nutshell. Now I will drop this whole because somewhere I don't require this. So this was the, so as per the Beer's law, absorbance is equivalent to kx. Fine. Now as per the Lambert's law, now the Beer's law, Beer ने कहा जो absorbance है that actually is directly proportional to the concentration. इस sample की concentration अगर ज़्यादा होगी it will absorb more. As per Beer's law, that is actually determined by concentration. तो हम दोनों को जब combine करते हैं, we'll end up with the Beer-Lambert law, that's absorbance, that is equal to K, C and X. And whenever the radiation falls on a sample, ultraviolet visible radiations, the energy is absorbed from it, not energy, the intensity of light which is absorbed from it, that is designated by A absorbance, that is a product of constant K, concentration of the sample and thickness of the medium. This is called in general the Beer-Lambert law. So when a monochromatic radiation passes through a medium, a medium which has a particular concentration C, which is concentration C, and this whole thickness is X. This whole thickness is X. So in Beer-Lambert law we can say when a radiation which has intensity I0, it passes through a medium which has concentration C and thickness X, that path length, and the intensity which comes out will be obviously less. So absorbance is given by KCX. Now this K is a constant. This constant is actually called as absorption coefficient. Okay? So this is called absorption coefficient. C is the concentration, X is the thickness of the path length. A हमने पहले भी देखा, we can also write this. A is basically log of I0 by I. K के लिए आप देखोगे कुछ बुक्स में एप्सिलॉन, ऐसे एप्सिलॉन CX, कुछ बुक्स में C. This epsilon is called as molar absorptivity coefficient, या molar extinction coefficient. So this K or this, it's called as molar extinction coefficient. मोलर एब्सॉर्प्शन कोएफिशिएंट और मोलर एक्सटिंक्शन कोएफिशिएंट। सो ये ऐसे भी हम लिख सकते हैं। अब एक टर्म यहाँ पे याद रख लीजिए, अगर हम ऐसे करें I/I0, it means fraction of the light that is transmitted intensity by this, so it's called as transmittance. This one it's called as absorbance, ठीक। और इसको थोड़ा सा आपस में कंपेयर करेंगे। ट्रांसमिटर्स में हम लिख लेते हैं इट इज I/I0, absorbance is log of I0/I। दोनों को हम मिलाएंगे, विल एंड अप विद रिलेशन T is equal to 10 to the power minus C। T is equal to 10 to the power minus C। अब आराम से इसको डिराइव कर सकते हो। मैंने शॉर्ट में कहा ट्रांसमिटेंस इज बेसिकली 10 raised to the power of minus A, बिकॉज इसमें लॉग फैक्टर है, और सेकंड इसमें इनवर्स रिलेशनशिप है। इसमें I/I0, इसमें I0/I including log in the absorbance. So transmittance lead to the absorbance. Transmittance and absorbance are not directly related. They're basically related through this relationship. Transmittance is equal to 10 to the power minus absorbance. ठीक है ना? So transmittance is basically 10 to the power minus absorbance. इसको भी आप याद रख सकते हैं। This is your transmittance T. This is your absorbance. So in general, from the Beer-Lambert law, we will end up with a conclusion. So we're ending up with a conclusion in the Beer-Lambert law. ये सब हम actually जहाँ पे पहुँचना चाहते हैं, that is this, that in Beer-Lambert law, we're ending up with a conclusion that if you have a sample which has a thickness x and the concentration of sample is C, when incident radiation is intensity I0, obviously it will absorb the radiation. The one which is coming out has intensity less I1, so your absorbance is given by the medium is given by epsilon C x. Now this can be called as Beer-Lambert law. So absorbance by the medium depends on the extinction coefficient. This is the extinction coefficient which is particular, which is specific for that particular sample or that particular molecule. ये हर molecule के लिए अलग होता है, multiplied by concentration, multiplied by thickness. This is Beer-Lambert law. यहाँ से हम कहेंगे epsilon is equal to extinction coefficient is A by Cx, ठीक। So यहाँ से हम derive करेंगे जो है एक term which is called as the extinction coefficient. Now अगर एक sample उसकी concentration है 1 mole, if our sample has a concentration that is 1 mole, molarity of the sample that is 1 mole, 1 molar concentration, ठीक, and thickness is 1 unit, that's 1 centimeter. So we can define the molar extinction coefficient as it's basically the absorbance. That's basically the absorbance of sample, absorbance of radiation by a particular sample whose concentration is 1 mole and whose thickness is 1 centimeter. So that can be, so this is, that becomes now molar extinction coefficient, 1 mole, molar extinction coefficient. So that's basically the absorbance by a sample when its concentration is 1 unit, and when its concentration is 1 unit, that's 1 mole, and thickness is 1 centimeter. So this is called as a molar extinction coefficient called epsilon. उसका unit हम निकाल सकते हैं। Absorbance जो है, जैसे हमने कह लिया, it's a log of I0/I, that's absorbance. अब दोनों intensity का ratio, that means this is a unitless quantity, ठीक? So that is A is a unitless quantity. C is, it has this unit of concentration, ठीक? So it is unit of concentration, that's mole per liter, and x centimeter. The unit of x, both this epsilon is, अभी C ऊपर जाएगा, that becomes C minus 1, x minus 1. So it becomes mole -1 लीटर, ठीक। मोल पर लीटर होता है, कॉन्सेंट्रेशन का, इट बिकम्स मोल -1 लीटर, क्योंकि C ऊपर आ जाएगा, X ऊपर आ जाएगा, so it becomes centimeter inverse. That becomes centimeter inverse. So this is the, और इसके बदले आप dm भी लिख सकते हो, right? You can write dm mole, so you write mole, this is the mole inverse, and then dm cube, centimeter cube, or decimeter cube, then centimeter inverse. So this is the unit of the molar extinction coefficient. Now this is all about the basics of the molecular spectroscopy, particularly the UV visible spectroscopy and Beer-Lambert law.